The next video that I want to do for you guys is just a reminder about what a limit is calculating. A limit is calculating a y value that a function approaches as x gets close to a specific number. So, for example, if I just said, what is the limit as x approached 3 of, let's try a relatively simple quadratic. Let's just say x squared minus 2. Okay. We could look at it graphically. We could just do it algebraically. Most of the time, if you want to know what y value your function is getting close to, you're going to actually figure out the y value that your function's actually going to be at. So if I want to know, if I looked at this graphically, x squared minus 2 would, oops, well, that didn't work either way. The stylus doesn't really aim very well. It would look like that. When x is 3, I know that the point actually does exist, and it exists at 7. And what the limit wants to know is, as I get close to 3 from either direction, so as I come in from the left or as I come in from the right, what y value am I getting close to? And the y value I'm getting close to is the y value for the actual point there. And so it would just be 7. But because this word is one of the key words in this definition, limits don't care if that point actually exists. If I took that very same function, and let's just say I removed the equation. Let's just say I gave you guys a random graph that looked like this. But let's say at 3, 7, let's say now there's a hole there. I can still calculate the limit as x approaches 3 of that function. Okay? Because the limit doesn't care if the point actually exists, because that's not what it's asking me. It's not saying, what y value do you hit when x actually is 3? What it says is, as x gets close to 3, what y value are you getting close to? And so the answer would still be 7. Okay? Now, what that would look like is a variety of things. Most of the time what you'll have is you'll have essentially one of two scenarios. You will be given an equation or you will be given a graph. And so the final video I'm going to make for you guys tonight is actually looking at the 5-2-1 homework, which most of those problems, at least on the front, were graphs that were given to you, and you were evaluating limits at different places. But let's say that I gave you this function. Okay, pretty standard exponential. If I were to look at it graphically, it would just look like that. And I could ask you a variety of things. I could ask you, what is the limit as x approaches negative infinity of that y, of the equation? And as x approaches negative infinity, this part right here, what it's telling me is that I'm headed left forever. And when I head left forever, this graph is going to get very, very flat, and it's going to approach 0. And it's really important that this is a limit, okay? I'm not saying y can actually hit 0, because we all know exponential functions never actually hit 0. We know they just get very, very close to 0. I could ask you, what's the limit as x approaches 0 of that function? And here's where x actually is 0, and that point does actually exist. As I approach 0 from the right and from the left, I am approaching that y-coordinate. And that y-coordinate can be generated just by actually plugging 0 into the equation. And the reason that it works is because this equation has no discontinuities. It has no holes, it has no jumps, it has no vertical asymptotes, it has no breaks in the graph at all. And so if you have a function with no breaks at all, then you can evaluate the limit just by plugging the number into the equation, okay? But you can evaluate some equations that do have breaks. Just depends on where they're asking you to evaluate the limit. So let's say that I gave you a relatively basic rational function like this one. Okay, relatively basic. Okay, there's no S step, there's no H step, there's nothing funky to do. Okay, I know that this rational function is going to have one discontinuity. It's not going to simplify and have holes. So the only other kind of discontinuity it could have would be a vertical asymptote. And that vertical asymptote is going to come from the denominator. And that means that it's going to exist at x equals 2. Okay, so the only place that this graph would have funky behavior is at x equals 2. Okay, so let's say I ask you, what is the limit as x approaches 0? Just because this is a rational function and it's going to have some funky behavior and we're going to have to do, the Schrady steps to analyze it and graph it and the whole 9 yards, that doesn't have any bearing at all. This graph, if you sketched it, if you just mentally pictured it, it's going to have a vertical asymptote here at 2. It's going to have a horizontal asymptote at 1. And so it's going to look like that. There you go. That's basically what that graph would kind of look like. So when x is approaching 0 from the left and from the right, it's entirely contained on this branch of the graph. There are no holes, there are no jumps, there are no other vertical asymptotes. So I can simply plug 0 into the equation and get my answer. So if I plug 0 into my equation, I would get a limit of -1/2. And you can see that is where that y coordinate would be when x actually is 0. Okay, now, since we've already got this kind of sketched, if I asked you to do the limit as x approaches +2 of that function, it's going to be does not exist. Okay, and there's two scenarios really that you're going to run into when you do a limit when you're approaching a vertical asymptote. Scenario number 1 is what you see sketched here. The two branches head in opposite directions. This branch heads down the vertical asymptote, this branch heads up the vertical asymptote. And since the two branches don't head to the same y value, so as x approaches 2, you are going 2 different directions. That makes the limit does not exist. Now, what OnRamps has said is that, let's say that I had a very similar function. Let's say I had a function that still had a vertical asymptote at 2, but let's say my two branches did this. That I actually had a t-step in my Schrady process and the whole 9 yards. And let's say this time we were asked to do the limit as x approached 2. Okay, so as we are approaching 2, from the left, we begin to shoot up towards positive infinity. As we come in from the right, we are once again headed up towards positive infinity. And what OnRamps has said is that any infinite behavior is automatically going to be the limit does not exist. So if you are headed up to positive infinity, if you are headed down to negative infinity, if you are diverging and headed both directions like the previous graph, it automatically does not exist. Now, I can tell you that when you get into calculus, they're going to ask you to determine what kind of behavior is being demonstrated as you approach 2. And so we do want to make sure that even though we're saying does not exist, that we understand that both branches are headed up to positive infinity, because that does tell us the behavior of our graph. Okay, we do know both branches are headed up. If both branches, however, had been headed down, then it still would have said does not exist as far as OnRamps is concerned. And the reason that OnRamps is saying that, you guys, is because positive or negative infinity, they're not actual numbers. You don't actually know how big they are. When do you actually get close enough to them? You might say, oh, I've gone down to infinity, 1 time or 2 times. 2 times infinity is still infinity. And so because it's not an actual number and you can't actually say where it is, then you still can't answer the question. What y value are you headed towards? Okay, but as far as the behavior of the graph, we would want to make sure that we understand the limit doesn't exist because it's headed down towards negative infinity in that case. Okay, and then really the final scenario as far as algebra goes, the equations and the things like that, I'm going to actually look at one of the equations from the S and the H video that I just posted. This was the first equation that I had worked, okay? So what you're going to see is you're going to see one of essentially two scenarios from this. This one's got a hole, and we know that already if you watched that S and that H video. But let's say you don't know that. Let's say you've never seen this equation before. I ask you to evaluate the limit as x approaches -1, okay, of your function. And so you think, okay, well, I haven't noticed the equation. I haven't done any Schrady steps. I don't remember there's a vertical asymptote there, which right now is what it looks like because we haven't done any simplifying. And so I go to plug -1 into the equation because most of the time that works. Okay, this is what's going to happen. You're going to plug -1 in on top and on bottom. And what you're going to get is you're going to get 0 over 0. Now, as far as Schrady goes, we'd already talked about this is indeterminate form. And literally what it meant in Schrady was it meant don't determine it in this form. Okay, and it told us that we'd missed a hole in our graph. Algebraically, it's telling us the same thing. Remember, limits don't care if there's a hole. So if limits don't care if there's a hole, then we need to be able to evaluate this limit still. And so what we would have to do is the same thing. We would simplify the equation. We would say, okay, well, we're going to do the limit as x approaches -1, and we're going to factor the numerator, and we're going to factor the denominator. We're going to cancel those x plus 1s out. And so really what we're evaluating is the limit as x approaches -1 of this now simplified equation. And now when I plug -1 in, I get -2, and I'm actually able to evaluate the limit. Okay, now graphically, remember what this graph would look like. We hadn't actually sketched it in the other video, but we know that this would graph as the line x minus 1. So it would have a y-intercept of -1. It would have a slope of +1. And we now know that we would have a hole at -1, -2. So graphically, this is what it would look like. So let's say you hadn't been given the equation. Okay, let's say you didn't know any of this. Okay, and you were just asked, what is the limit as x approaches 1, or -1 rather, of this graph? Well, remember that limits don't care if holes are there. So as you approach from the right, and as you approach -1 from the left, you are approaching this y value, and that y value is -2. And it doesn't matter that you don't actually hit that point, that it's not a solid dot. Okay? So I hope that helps you understand. Oh, I guess I'm going to do one final example just because I don't know how many of you are going to also watch the explanation of homework 521. If you have a jump in the graph, so this one you have to be given, well, you either have to be given as a piecewise equation, which I don't think we've seen all year. But let's say I give you this line, and let's say it 1, 2, let's say this is a 3, 3, and then let's say, so let's say I give you a really simple piecewise graph. Okay, and this is what homework 521 this starts out with. It gives you graphs that have things like this. They've got jumps, they've got holes, things like this. Okay, what they're going to do is they're going to ask you a couple of different things, trying to help you understand that the limit as x approaches 3 of this particular function it's going to be does not exist, because what it's asking you is what y value are you approaching as x gets close to 3? Well, as x approaches 3 from this direction, you're approaching a different y value than when x approaches 3 from this direction. And that's why the answer is does not exist. So what the 521 homework is going to do is it's going to break it down into pieces for you to help you try to figure that out. So what they start you out with is they'll ask you something like, what is the limit as x approaches 3 from the positive side? So this is from the right, okay, or from above 3. That's why it's got the positive, okay? And so you go to the right of 3. That puts you on this section of the graph. You turn around and you head back towards 3. And as you head back towards 3, you are approaching this y value right here, which is at 4. Then what they would do is have you do the limit as x approached 3 from the negative side, which is from the to the left or underneath 3. So this is from the left. It's what we call a left-hand limit. Okay, and the first one was a right-hand limit. And so you go to where x is 3 and you go to the left of it. That puts you on this section of the graph now. And you turn and you head towards 3. And as you head towards that x value of 3, you are now approaching this y value, which is also 3. And the fact that these are not the same, these are different, is what confirms, or what tells us ultimately, that the limit as x approaches 3 of our function does not exist. In order for this to actually exist, these two numbers right here have to be the same. You have to approach the same y value from both directions. Okay? Now, one other thing they do ask you, which I'm not sure if anybody's been struggling with it, they will actually ask you, okay, where actually is y when x actually is 3? And that's just asking you, where is actually the solid dot? When x actually equals 3, what is y actually? And it is 4. But that has nothing to do with the limit. Okay? So I hope that helps. Look forward to one more video.